Hi everyone, I'm Shravya Kondrakunta. I'm going to give a presentation on my paper, The Rational Selection of Goal Operations and the Integration of Search Strategies with Goal-Driven Autonomy. Hopefully everyone can see my screen. Hello?
Yes, we can see it.
Okay, thank you. Before I start, I would like to thank all of my co-authors from different universities. And in addition, I would also like to thank the NSF and ONR grants, which funded this research. So here is a brief outline of my talk. First, I'm going to introduce you to what an intelligent physical system is, and then I'll talk about the frameworks that we have developed to implement such a system. And then I'll talk about the problem domain in which we have implemented our work, then present some search strategies in that domain and give you a working example and present you with empirical results and conclusion. If you guys were attended the goal reasoning workshop, we presented an extension of this work in the workshop. So some of the slides that you might see here could be similar to that talk. We claim that an intelligent physical system must have these four capabilities, the capabilities of perception, thinking, action, and communication, meaning it should have the ability to gather information about the world that it is working on with perception, and after getting all the information, it should be able to think or generate goals based on the information, and then it should be able to achieve those goals in the real world through actions. And finally, it should be able to communicate its thought processes or the steps it takes to achieve its goals to either a human expert or maybe several other agents in the domain. So while developing these kinds of agents, the two main issues that we face are unexpected events in the real world, as well as partial observability. Unexpected events meaning, let's say I have a robot and I ask it to kind of switch on the light in this room, and a person comes in and achieves the goal for it. It shouldn't be. It should be able to incorporate that change and shouldn't try to pursue that goal again, right? So all those kinds of events and partial observability, this is something that we humans face as well. We are limited by our by the scope of our perception. Let's say if we are sitting in this room, we will be only knowledgeable about the events happening in that room, and so whenever we go out, we should be able to kind of incorporate all the changes that are happening outside and maybe modify our goals based on the new information we obtain. So some of the examples of these intelligent physical systems are either self-driving cars like Waymo, or humanoid robots like Simon and Sophia, and etc. So out of all the four capabilities, we are primarily interested in the thinking process or goal achievement. So let's talk about the approach that we have developed to implement such an agent. So we think that there are three layers to it. The first one is the control layer or control-driven autonomy layer, which is at the ground level, and it has all the physical systems in it, meaning the robots with all the actuators and all the working parts that you can see in the real world, or it could also be a simulator that simulates an actual robot. And this from the control layer, we would get inputs to the agent, and we believe that the agent must be able to generate some kind of beliefs based on the inputs. The inputs could be either the camera inputs or inputs from several sensors of the agent and all that. And the agent should be able to kind of process this data and generate some kind of beliefs and kind of store them in their memory. And then on top of the belief layer, we have GDA layer, which can get these beliefs of the agent, and also in addition, it has its own knowledge of the world. And by comparing these two, it should be the goal-driven autonomy layer should be able to make decisions and should be able to perform actions both on the belief layer as well as the control layer. So although we apply this approach in just a marine environment, but we think that this structure is general enough to be applicable to several other domains as well. So in GDA, we have developed several goal operations which kind of mimic human performance a little bit to kind of emulate this intelligent behavior in a physical system. So the first one is goal selection operation. I mean, more often than not, like whenever we are talking about robots, we usually are moving towards a world where we give the agents multiple goals at the same time, and the agents must be able to figure out or order the goals based on its own situation. So let's say I have a house robot and I gave it a bunch of chores to achieve, and I cannot expect to stay around for the robot to complete each task, right? It should be able to pick and order the tasks on its own. So we term this kind of operation as goal selection, meaning like choosing one goal at a time to achieve. We also have goal formulation operation, meaning let's say if the agent is working on something and an unexpected event or something, an emergency event like fire erupts in a room beside it, then when a human is not around, it should be able to kind of figure out the steps to keep itself away from the harm's way, or all those kinds of things. And in addition to this goal formulation operation, we have several other goal operations as well, like goal change, goal monitors, and goal delegation. But we are not going to discuss too much into the remaining operations because that's not the focus of this paper. We are only going to talk about selection and formulation in this one. So whenever an agent is working in the real world, there are multiple, most of the times these operations do not happen in a sequential manner. Most often there are situations where when these goal operations co-occur. Again, in our scenario, we are just focusing on selection and formulation. So let's say our agent is working on its chores, and again, to reiterate on my example, a fire erupts in a room beside us. It hears a fire alarm, and should it now continue to work on its goals, like on its selected goals, or should it just abandon them and go deal with the fire first? I mean, yeah, it's complete. If you think about it, it's completely dependent on the situation, right? Let's say if the fire is because a naughty kid kind of lights a match near the fire detector, then it shouldn't kind of run with a fire extinguisher to the other room to put out the fire, right? And let's say if the fire is actually due to some kind of short circuit or something, then it should kind of take an appropriate action, right? So everything is dependent on the situation, and the agent must be able to observe all the changes and must act according to the situation that it is in, right? So in order to kind of tackle these kinds of situations, we have presented an algorithm in our paper, so which is fightable essentially, and it has it takes an input as the state transition system. It observes the current state. I do not know if you can see my mouse, but SC is the current state, and SE is the expected state that the agent thinks that it needs to be in, and GC is the current goal that the agent is working on right now, and G hat is the entire goal agenda of the agent. And based on its current observations of the state and expectations of the agent. If these two do not match, then we assume an anomaly is detected. In this kind of scenario, an agent either can come up with a goal, like formulate a goal to tackle the anomaly, or it can either select a goal to continue its work, or kind of abandon its selected goal and come up with and select a new goal altogether. So within these two choices, we have written a goals affected function, which is domain specific and is also kind of expert given for expert tailored specifically to fit in all different kinds of anomalies happening in the domain. And based on this, let's say if the selected goal is kind of in the affected goals list, then it gives priority to formulation. If not, then it gives priority to selection operation. Again, we have kind of extended this work to fit into more domains on our workshop paper. You're welcome to take a look at it. So just to talk about the domain in which we have implemented our work, we call it the marine survey domain, and it is an actual real world domain where we have this Grace Reef National Marine Sanctuary area. And these marine scientists catch these fish, tag them with an acoustic transmitter, and leave them back in the ocean. And they want to actually survey the entire region to study the fish habitats and also kind of gather measurements around the environment for various purposes, one being environmental conservation. And so yeah, these are the actual coordinates of the Grace Reef National Marine Sanctuary area, and we are attempting to use underwater gliders to survey this region. And the pink area is just a research only area, meaning general public is not allowed in that region. So usually the missions last for 1 to 2 months, meaning the agent is within the water for 1 to 2 months. And once the agent goes into the water, it can only surface once every 4 hours. And even after its surfacing event, it can only communicate with a human expert if a surface vessel is nearby. If it cannot find a surface vessel nearby, it needs to use a satellite communication, which is very costly. And yeah, so before actually implementing our work onto the real world gliders and everything, we have simulated, we tried to simulate our work using a simulated environment, and we have used Moose for it. It is an open source available software developed by MIT and Oxford specifically for underwater platforms. So we have divided the entire region into 25 cells, and the red object here is our agent Grace, and the gray area around it is its sensor. We'll talk about the domain in a bit. So here are the actual robotic fish, robotic gliders that we intend to use to implement our work in the real world. So on the left-hand side, the fish are from are courtesy of NSF project developed by Dr. Jabotan, and on the right side are the underwater gliders manufactured by Teledyne Marine. And the goals in the domain are to gather measurements about the water using the sensors like temperature, salinity, pressure, and everything. And also other goals are to discover hotspots in the domain, meaning the areas where fish concentrations, highest density of fish exist. And again, a long-term goal is to track the movement of the fish underwater as well. And the problems that happen or that occur in this domain are remora attacks. These are the remora are these kinds of fish which come and latch onto the gliders thinking them to be an actual fish, and they kind of hinder the movement of the agent by drifting it to one side or one direction. And there are blowout situations that occur in the real world, meaning there are flow sometimes just throws the glider into open waters, and we do not want that happening. And there are obstacles underwater with the coral reefs and everything. And there are also shark attacks, and we do not have a way to deal with it yet. So in order to survey the entire region, we have developed 3 specific search strategies. The first one is structured search, which uses a greedy approach, a stochastic hill climbing algorithm. It just samples every cell and kind of goes to the nearest cell where it thinks there is a good possibility of finding a hotspot among all of its adjacent cells. And excuse me. And there is ergodic search, which is a control driven search strategy, and it kind of averages the spatial distribution of the information and picks and chooses the next location that it can go to. And there is also also we have combined these 2 search strategies into one search strategy, and we call it structured search combined with ergodic search. And it kind of uses the greedy approach as well as the control approach. Again, I'm not going to go into too many details of the search strategies. We have presented several results based on these search strategies by comparing each of them in our paper. You're welcome to take a look at it. So let's now take a look at a working example in this domain. So just to give you a brief overview of the domain, once again, we have divided the entire region into 25 different cells, and the red tiny dots that you see are fish. And we currently assume them to be static because there are some compromises that you need to make when you work in a simulated environment, right? So yeah, we currently assume the fish to be static, and the red line across along the edge of the cell is a hard obstacle, meaning it cannot pass through that obstacle even when it tries to gather some information. And there are also green obstacles, meaning if the agent spends a little bit of time to gather information on the obstacle, it can either dive up or dive down and can pass through the obstacle. And there are also we simulated the remora attacks as long pauses in this domain. So whenever you see a long pause in the demo, it's because it's probably dealing with a remora attack, and the agent needs to fly backwards to kind of get rid of remora. So that's a solution strategy that it needs to employ to get rid of remora. And so again, we have multiple sensors on board, and so whenever the fish falls within the range of the sensor, the agent will be able to detect the fish tag. So the goals are to survey all the 25 locations in this domain. So yeah, the agent is now surveying the first location, and it encountered an anomaly. Now it encountered an anomaly, but it thought that it doesn't have to deal with it, and it kind of prioritized selection over formulation, and it has chosen a different location to go to. That long pause is the remora attack, and it chose a second location, and it surveyed the location, and it encountered an anomaly again. And since it is repeating more repeating more often, it thought that it needs to gather more information about it. Hence it the straight line that you see is the agent kind of trying to gather more information on the anomaly. And yeah,
5 minutes.
Oh, 5 minutes. Okay. So again, it encountered an anomaly again, or the obstacle again. So it tried to gather information, and it thought that it can pass through. So it has passed through, and yeah. And so eventually it will kind of do all the goals. So currently, we assume that there are 1,000 fish tags in the domain, and Grace begins surveying at 100 different initial starting locations within these 25 cells. So we essentially have like 2,500 data points, and the anomalies are again Remora attacks, blockades, and flow. Again, we did not have a way to represent flow anomalies as well, but they do occur in this domain. And the performance metric, I'm sorry, Pat, but we also use F1 scores, although we do present precision and recall. So to compare our agent's performance, we have generated, we tried to compare our agent's performance against an agent which tries to always give priority to selection, and a second agent which always tries to give priority to formulation. So here are the results that we have got. And again, there are a bunch of other intermediary results that we have presented in the paper. So as you can see, our ASGO agent performed really well over the two other agents. And so in conclusion, again, all of our work is openly available at the following link, and most of our work is still in very preliminary stages. And but combining all the field trials as well as the simulation studies, we think that it would really advance the field of intelligent autonomous agents as well as goal-driven autonomy. And we think that more work on belief spaces could integrate the cognitive architectures as well as control architectures better. And once again, for future, we would like to include several other goal operations like goal change, goal delegation, and all those into the decision-making process of an agent, so that we can truly develop an intelligent autonomous agent that can work robustly in a real-world setting. So yeah, thank you. I can open up for questions.
Thank you, Shravya. Do we have questions? I didn't see any on Slack yet, but we'll look again. Why can't anyone want to raise their hand?
I want to know how Remoras will attach themselves to a robot fish.
Yeah, so the Remora, they what to say, they're not gills actually. They are structured. I mean, they are these fish that kind of latch themselves onto. Is it a joke, by the way?
Well, I mean, no, I know they're eels, and I know that. But how do they latch on to into a robot? I mean, don't they have to sink their teeth in? It's not.
No,
it's not crucial to your research. It's just curious.
Yeah, sure. So they just, I mean, they just have this kind of suction things on the bottom of their body,
Got it.
and
Got it.
it's not teeth. Yeah.
In your evaluation, you were comparing your agent to other agents. What was the difference again? It was, were you ablating the goal change mechanism?
Yeah. So so what we did was we developed two other agents, and since we are essentially only comparing two operations in this work, so we generated one agent which would always give priority to one operation at a time. So we have developed one agent which only prioritizes selection, and then a second one which only prioritizes formulation.
Okay.
Yeah.
And you have several other kinds of operations that
Yes.
you didn't go
Yes.
into. Do you anticipate that they'll have a significant effect, or?
Yes, yes, we do. I mean, yes, and we actually, I mean, extended this work. I mean, more immediate extension. We have actually presented it in our workshop paper. We included goal change operation in that work, and also, yeah, the results were very interesting, and yeah, yeah.